Well, welcome to this short little expose on basic probability. As with all basic problems, you still need to determine what you know. You need to find a tool to solve your problem to determine what you want to find out. Now, with basic probability, there are some things you need to sort of track down. First of all, based on the various events or occurrences that you're trying to define or identify, it's helpful to determine whether they're mutually exclusive. Well, in other words, if event A happens, that means event B cannot happen. Or if event B happens, event A cannot happen. Those would be mutually exclusive events. Um, but there are also ways to handle events that are not necessarily mutually exclusive. I'll try to do one short example for that. When you look at total probability, you need to determine whether you have a collectively exhaustive set of information. That means your solution is looking at all the possibilities, collectively exhaustive. If you don't have a collectively exhaustive set, then something unknown or unexpected can happen. That's usually what happens in the economy. People never work with a collectively exhaustive set. It's also nice to determine whether your events are independent of each other or whether they have some dependency on one event or another happening. So we're going to take just a quick traipse through the land of basic probability with a couple of examples, including one on selecting a used car and another on the lottery. So hang with me and we'll see if we can get through this in our 15-minute YouTube limit. So the first thing we're going to look at is selecting that used car. Let's say, for example, it's going to be what we're going to call conditional probability. The probability that something happens given that something else has happened in the first place. And what we have to do is use basically what's called the conditional probability relationship, and that is stated here like this. The probability of event A happening, given that B happens, is equal to the probability of A and B happening divided by the probability that B happens. Okay? Conditional probability. Very important. And let's say you go to the used car lot, and the used car lot dealer tells you that of all my cars, okay, 70% of them have air conditioning. So the probability of AC is equal to 0.7. He also says that 40% of them have a CD player. And he also tells you that the probability of cars having both is 0.2 or 20%. Probability of AC and CD equals 0.2. Now let's say you're interested in having a car with both, of course, but there are other criteria that come into play. So let's say you want to determine the probability of the car you pick having a CD player given that it has air conditioning. So what fraction of that set is going to have the CD player given that it has air conditioning? Well, we know that the probability of both is 0.2, but that's a slightly different probability. We can take this basic equation and, oh, by the way, in your basic formula sheet, that equation is identified as equation 5-6 on your formula sheet. You'll notice it's algebraically arranged a little differently, but you can do that with these various equations. You can use the rules of algebra to rearrange them. So, if we want to find out the probability of a car with a CD player given that it has AC, well, it's simply the probability of both, 0.2, over the probability of B, that one, AC, or 0.7, which is about 0.28. Okay, and it's that straightforward. So we're going to use this basic relationship now to talk about the lottery and extend that on into some finance rules called expectational analysis. Now, the last time I looked at the lottery, the basic Texas lottery was structured so that you pick 6 numbers out of a bucket of 54. They put 54 ping pong balls with different numbers on them, and then they'll randomly pick 6 numbers out, and that's without replacement. Without replacement. That makes each pick independent of the previous pick. Okay? That's probability stuff. That's an important identifier. Is one event independent from the other? And for the lottery, it is. So we can then use our basic relationship of conditional probability. It's called the multiplication rule for 2 events when they're independent. The multiplication rule for 2 events when they're independent. And we know that our basic rule is that the probability of event A and B is equal to the probability of event B, given that A has happened, times the probability of event A. And we're going to let A be our first pick. One of our numbers shows up, and B be, on the second pick, the probability that another one of our numbers shows up, and these are independent. We can further simplify this to say that the probability of A and B in this event, if they are independent events, if event A and event B are independent, is equal to simply the probability of A times the probability of B. Okay? Pretty straightforward. Okay. So, let's use this for the lottery. 6 out of 54. And let's say you've picked your numbers. Okay? What's the probability that one of your numbers will be picked as the first ball? That's the way we have to look at it. So the probability of A that one of your 6 numbers will be picked is 6 over 54. Okay? Now, given that your first number got picked, what's the probability that you pick A and B, or one of your numbers is picked on the second one of your remaining 5? Well, the probability of B, given that A has happened, is equal to be 5 over 53, right? And then we can go back to this relationship when we say that the probability that both A and B happens is equal to 6 54ths times 5 53rds. That's the probability that out of those 6 numbers, 2 of them will be picked that you have selected as your lucky numbers. Okay? Well, we can continue this on out for all 6 numbers. Each draw is independent from the previous draw, assuming that it's done without replacement. I don't put one of those numbers back in. A number can only be picked once, then it's set aside, and the remaining numbers are used to pick the second draw and the third draw and so forth. So, when we look at this now, we're going to say, what is the probability that all 6 get picked? Well, the probability of A and B and C and D and E and F is going to equal to 6 54ths times 5 53rds times 4 52nds times 3 out of the remaining 51 times 2 out of the remaining 50 times 1 chance out of the remaining 49. Well, let's go ahead and multiply this out and see what we got. Okay, let's see. Well, we'll set it up like this. 6 times 5 times 4 times 3 times 1 is equal to 6 factorial, which is equal to 720. Okay, you got that? Somebody asked, what does that symbol mean? Factorial simply means I take the starting number, 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. 100 factorial will be 100 times 99 times 98 times 97 and so forth. That's a very large number. Okay, and if I multiply all this out, I've got 54 times 53 times 52 times 51 times 50 times 49, and what I come up with is, and I'm going to round this one off a little bit, 1.8596 times 10 to the 10th. Okay, that's a pretty big number. Now if I simplify that, that'd be 7.2 times 10 squared over 1.8596 times 10 to the 10th, and let's see. Okay, it's about 1 out of 25,827,000. Okay. So your odds of winning the jackpot, if this is the structure for the lottery, is 1 in 25.8 million. Pretty good odds, huh? Is that worth your dollar? Well, that's sort of the next phase of this. Is that dollar worth it? And when we look at the value of the dollar, we want to say, what is the expected value of my $1? Well, in the case of the lottery, it would be the jackpot size times the probability of winning the jackpot. Okay? And I want my expected value of $1, if I'm applying finance rules to this lottery, I want my dollar to be worth, well, $1. So, in order for this to come out to be $1 as the expected value, I need the jackpot times 1 over 25,827,000. I want the jackpot to be at least $25,827,000. Okay? At this point, I can begin to think that my $1 investment in the jackpot is worth it, because the probability of winning times the size of the payoff is equal to my dollar. In other words, $1 invested has an expected return of $1. Naturally, if the jackpot gets bigger, the expected value of a ticket rises, and then I start exceeding that. But wait, I've got to figure out some new stuff here. First of all, that 25 million has a time value of money attached to it, doesn't it? Because the way they work this out is they take this $25 million jackpot and they stretch it out over, say, 20 years. You'd get about 1.25 million a year for 20 years. And if you do that, then that's about $25 million. So you all know that time value of money makes that 25 million stretched out not quite worth 25 million. I'll leave that as an exercise to determine what 20 equal payments, divide 25.8 million by 20. You're basically going to get a present value of about 12 million given standard discounting factors of, say, around 4 to 5%. So if you got the 12 million as the present value, then my dollar given up today, I'd want that to equal the 12 million. So to get me 12 million today, yeah, 25.8 million over time wouldn't quite make it, because my odds are 1 out of 25 million. I basically need to double the jackpot to about $51.7 million in order to make it worthwhile today. This is starting to get really tricky. But wait, we forgot about Uncle Sam. Uncle Sam's going to take 40 or 50% of that 25 million over time, and even if I take the lump sum options, he's going to take a bunch. Hey, Buy a lottery ticket if you like.